So, our weather briefing today. My name is Liliane Hofer and I'm working at the ZAMG, at the Central Weather Service of Austria. And yeah, here you can see me. And I am sitting in Austria, but not at Vienna, at the headquarters of the ZAMG, but at Salzburg. You can see the logo here. I'm sitting here. And now could you please take your stars and put it to the location where you're sitting at the moment, so we get a quick overview. And if your country is not on the map shown here, please put the star over here. You can either put the star over here or write it in a text chat if your country is not on the map. Okay, I see the first stars. So we have people from Spain, Great Britain, Germany, Austria, Southeastern Europe, Italy. Yeah. Okay, so I think everyone has put his star there. So people from all over Europe. So I hope we managed to get an overview over all the weather you're currently looking at the moment. So would like to start with water vapor 6.2 image, because I think the water vapor image is always a good point to start. Because yeah, you get a quick overview over the dynamics in the upper atmosphere, and so it's really a good starting point. So I would like to make the weather briefing not alone, but with the help of you. So I would like you to take again your stars, your pointers, and show me where do you think that the low pressure centers are located in that image. So you see the structures, you see the clouds. Where do you think any low pressure centers are located? Okay, fine. The one near the Iberian Peninsula. Yes. In the northeastern part. Okay. Any other idea? Any more low centers? Take a look at the dark stripes, at the cloud formations. What do you think? Any other low? Okay. Northeast of Iceland. Okay, I think that's it. Some last star anywhere? No. Okay, so let's take a quick look at the geopotential height in 500 hectopascal and see whether you were right. Okay, so the low over here, there were many stars in that area, so that's true. There's this impressive low. Then there were some stars in the northeastern part. There is a low and another low center over here. There was one star, totally correct. You probably missed this low over here. I mean, it's more a trough than a low, but yeah. So that's the current weather situation, or at least yesterday. You see the images from yesterday, 12 UTC. So we have this impressive low near the Iberian Peninsula, another low over the Aegean Sea, and this ridge over western to central Europe. So we can more or less say we have kind of an omega constellation over here. It looks like the Greek syllable omega. We have a pronounced trough over here, another trough over here. So yeah, and some frontal cloud bands in this area. So there's a lot of weather going on, also some nice weather over here, and that should be our starting point. So now we know with what dynamics we're dealing with. So let's go a slide further. So we're still at the water vapor image. We still start with that one. It's still 12 UTC, and I want you to concentrate on this area of the image. So you see the frontal zone extending from the Atlantic over the northern British Isles to Norway and Finland. And in this area you can see this more or less pronounced cloud bulge. So I was thinking, okay, that could be something that could develop more, and just wanted to know what are the models thinking of this cloud bulge. So you can always compare the real water vapor image to the pseudo water vapor image. That's an image that is computed from the ECMWF model. You can also find it at the ePort, and it looks like this. If you remember the other structures, I will toggle a little bit back and forth. I hope the internet connection is so good that you can see it in time. If you now just concentrate on the other structures, on the low over here or the low in the northeastern part of Europe, you see that the computed satellite image is nearly as good as the real satellite image. So you have the structures over here, the low over here. So the model is really, really strong. So the performance is really good. But in this area over here, you can't see the cloud bulge. So the model is nearly perfect, but not 100% perfect, because it misses this cloud bulge, and that it could be important. It could develop even more. And so, yeah, that's always nice, because I know the Atlantic there are not many people living there, but if this would occur more near to Europe, then it could be of importance. I mean, it may also be of importance over here. And one reason that the model can't see it is probably because there are not so many observations over the Atlantic. But it's always good to compare the real situation to the model situation. And you can always do this with satellite images, because you get a quick overview over vast areas. So, okay, so the model satellite field doesn't show us this cloud bulge. So we'll take a quick look at the equivalent thickness, which is always a good sign for fronts. And you see here, it looks like mainly cold front. You see the cloud bulge in the background, and yeah. So also the equivalent thickness shows no sign for any development, for any wave development over here. So, okay, the model might miss this. So as a forecaster, you should always keep your eye on things like that, because that may always be of importance. So as we have the equivalent thickness here, let's take a deeper look at the other structures. And I would like to concentrate now on this area, the Iberian Peninsula, Northern Africa. So you see this distinct low and this pronounced thickness ridge over here. And it's getting spring, or it is spring, the temperature rise, and so we have to switch from winter forecasting mode to summer forecasting mode. So convection gets more and more important these days, especially at these latitudes over here where it is already warm. And so you see thickness ridge. If you have such a thickness ridge during summer, you always have to think of convection. And there are some tools that may help you forecasting convection, some satellite tools. For example, the GII, the Global Instability Indices. I don't know whether you have seen such an image before. I hope so. You can also find it at the ePort. And the GII computes the stability or the instability of the atmosphere. And this method can only work over cloud-free areas. So that's the reason why the information, the colored areas are not over all Europe. You see in the cloudy regions, the values cannot be computed. And here the GII you see here is the lifted index. And there you see which values it can take. And in the region of the thickness ridge, at least where the GII is available, you see blue to greenish values. That means quite negative values, and that is a sign for instability. So if you have a thickness ridge and GII showing unstable conditions, then you can be sure that something will happen in that area. So the GII is always a good tool. It shouldn't be used as a standalone, at least that's what I have seen in the last convective seasons, but it's always a good bonus tool. So if you have a thickness ridge and instable GII, then yeah, you have to be careful. You have to take a closer look at that area. But it's always a good tool to use. So, okay, let's take another look at the situation with the help of the EMAS RGB. The EMAS RGB is a combination of several water vapor and infrared channels. Some brightness temperature difference are computed and used, and the result is an image that shows you air masses. So the bluish colors, they are assigned for polar air masses. Green to orange colors are assigned for tropical air masses, and the reddish colors, they are most important because they show PV anomalies. So PV anomalies where stratospheric air is protruding, and they are always assigned for cyclogenic developments that could go on in this area. Or they are also assigned, like in this case, for the jet streak or for troughs, if you remember this trough over here. So the reddish colors indicate this trough, and you can also see these showery conditions over here. So it's always a good tool, the ERMAS RGB. And I want to stick to the low over the Iberian Peninsula, and you see some orange color over here, which may indicate the jet streak, but you can also see some bluish colors. So this is a sign for polar air masses, and it means that probably the Iberian Peninsula is not facing the best weather conditions at the moment. And yeah, it's probably also a little bit too cold for the season. What more can you see in the EMAS RGB? If we now concentrate on the cloud fields, you see some very bright cloud fields over here, east of Scotland, but also south of the Alpine Ridge. And these clouds are Lee clouds. So if you know the area a little bit, I mean, okay, here are the Alps. I want to highlight it. I'll take this one. Here's the Alpine Ridge, and here is Scotland, and there are the Southern Highlands in that area. So we have winds coming from the western directions, and in the lee of the mountains, these lee clouds form, and on the Alpine Ridge we have wind from northern directions. Then we have an area where no clouds are, so what we see here is a kind of a hydraulic jump, but quite interesting to see here. And I want to take a closer look at these phenomena, but not with the help of the EMAS RGB, because the EMAS RGB has another purpose. I mean, you can detect clouds here, but there are better satellite images, better RGB combinations, and so we will take a closer look at these Lee clouds with the help of the day microphysics RGB. You can see here many colors. It looks quite nice, this RGB. But as the name says, microphysics RGB, you get some information about the microphysics of the clouds, and that's one reason for the different colors. And if you look at the Lee clouds, also east of Scotland, but also south of the Alps, they look kind of bright orange. And the reason for this bright orange color is that orange is a sign for optically thick clouds, or thick clouds, and the brighter the color, that means that smaller particles are in that cloud, and it's a sign for really small ice particles that are part of these Lee clouds. So if you compare the Lee clouds to the other clouds, they are more reddish, and yeah, they look quite special, so to say, this Lee cloud. So day microphysics RGB is always a nice RGB to use in order to see what clouds are where and if they're optically thick or thin, and also take a closer look into the microphysics of the clouds. It's always a good tool to start. So let's jump a little bit. So the last image we've seen was from yesterday, 12 UTC. Now we are here 6 hours later, so that means yesterday 18 UTC. We're still, or again, looking at the water vapor 6.2 channel, and I've told you about the thickness ridge over northern Africa and the Iberian Peninsula, and we've seen the GRI, the lifted indices, showing us a quite unstable atmosphere in that area, and you see some more convective cells have developed over here, and it looks quite convective over there. So as I told you before, the GII is always a nice tool for forecasting convection. Okay, now again, 12 hours later, it's already today now. It's again the water vapor 6.2 image. You see still some convective development over here, but I want to take again a look at the cloud bulge over here. You see it has developed even more. It's now quite pronounced, and yeah, we will take now a look at the pseudo image, if the pseudo image now also shows this cloud bulge over here. But before we jump to the model satellite image, take a quick look over here again, Scotland. We still have these Lee clouds. I hope you can see it. They are more whitish than the other clouds surrounding. And the interesting thing is that if we now take a look at the pseudo water vapor image, the model also forecasts Lee clouds. So the ECMWF model is really quite sophisticated. But now, again, jump to this area, jump to the Atlantic. You see the model now forecasts this cloud bulge, and if you trust the satellite images, what you always should do, because they show the real situation, you had the information about this cloud bulge nearly 18 hours earlier. So yeah, it's always a good thing to compare the model to the real world. And if we now take a look at the infrared image at this time and the equivalent thickness, you see that now also the equivalent thickness shows some kind of wave development going on over here. Okay, so that's the current weather situation. You see again the Lee clouds over here and some nice high pressure system over Western to Central Europe, the Mediterranean area. So we really have spring conditions over here, which is not too typical for April, because April weather has a very bad reputation for unsettled weather conditions. And so I want to make a small retrospect. What's the April weather, what happened so far? So what April 2015, how did it look like so far in mine? Okay, yeah, it's always nice to get tennis rackets out in April. We had some snow over here in Austria. I have to admit, Easter was quite snowy. We had lots of snow, nearly 1 meter of snow fell in the Alpine region. So it gets normal that we may have more snow at Easter than to show you the nice side of April. And so I want to jump a little bit, not only from time but also from place. So we're here at the Middle East ePort. It's the beginning of April, the 2nd April, 0 UC. You have the infrared 10.8 image, and now what do you think? What would you like to tell you about? In what region do you think is an interesting phenomenon going on? Please take your star and choose a location where you think this could be quite interesting. What do I want to show you? Okay, so you are either shy or you have no idea what I want to show you. Okay, some first stars. Okay, so most of you are concentrating on the slow over here, on these clouds. Okay, some stars over Saudi Arabia. Yeah, I think it's quite a tricky one because in this image you don't really see what I want to show you. But that's, yeah. It gets more obvious if I show you the next image. And now I think everyone knows what I want to talk about. This is the dust RGB, and it shows you a major dust outbreak over the Arabian Peninsula. Yeah, so now it's clear. And some of you pointed to the low, and this low kind of steered up the dust along its path, and now you see from the color spectrum extends from bluish to pinkish colors. It all shows the dust, and the colors depend on the height where the dust is located. So the dust RGB is really powerful. You compare it to the infrared RGB in the slide before, you could see nearly nothing in the area, and now the dust RGB shows you in really bright colors. There's lots of dust in the air. And that's the reason why I want to go a little bit more into detail concerning the dust RGB. So dust RGB is probably the wrong name for this RGB because it is really a powerful tool, and the name dust RGB is probably a little bit of understatement because it can show you so much more than just dust. For example, it's also a good RGB to look at if you want to detect thin cirrus clouds. And so here I show you kind of the recipe of the dust RGB. It mainly consists of brightness temperature differences of infrared channels. So on the red channel, we have the brightness temperature difference of the infrared 12.0 and the infrared 10.8 channel. So those two channels, infrared 12.0 and 10.8, are the so-called split window channels. So each of the two channels respond to the temperature of clouds and surface, but each channel has a slightly different response. So, for example, for dust, the brightness temperature difference is always positive. It's always greater than 0. So you have a big red contribution. If there's dust in the air, this RGB gives this brightness temperature difference gives a big red contribution. On the other hand, I've told you the dust RGB is also good for monitoring thin cirrus clouds. For cirrus clouds, this brightness temperature difference is always negative. It's always in this area, so we have nearly no contribution from the red channel. On the green color beam, we have the brightness temperature difference between the infrared 10.8 and the infrared 8.7 channel. So the 10.8 we've heard before gives us information about the cloud top temperature or the surface temperature, and the 10.8 channel is mainly used to provide information on thin cirrus clouds. So if you have dust in the air, this brightness temperature is nearly 0, so we have no contribution from the green color beam. If you have cirrus clouds and no dust, then this brightness temperature is negative. So again, you have nearly no contribution from the green color beam. And the blue color represents the infrared 10.8. So again, temperature information. And the cooler or the lower the temperature, the less the contribution from this color beam. So for cirrus clouds, which are in the upper atmosphere and therefore really cold clouds, we have low contribution, and for dust clouds, it depends in which height they are situated, we have low to medium or sometimes even high contribution. So that's the reason why dust appears bluish to pinkish, because it mainly consists of red and blue. Whereas cirrus clouds have no contribution from any of these channels, or just low contribution, so cirrus clouds appear black. Okay, that was a theory so far, and you can detect the dust also with other satellite images, but it's not that pronounced. For example, here we have the visible 0.6 image. It's now 6 UTC in the morning, and yeah, you can see the dust, or you how should I say, now you know there is dust. You can clearly see it, and probably the best picture you get of it is over the ocean, as you see these dust shades. But I think if you don't know where to look for the dust, the visible might not be the best starting point, the visible channels. A little bit better to see is the dust in the natural color RGB. On the red beam there's the near infrared 1.6 channel, which is quite reflective for soil, and so you can see the dust here as you would in the color as you would assume it. If you compare it to the bare ground over here, you see a difference, and it's always very visible over the ocean areas. But in the end, if you compare it to the dust RGB, it's always the best solution to choose in the case of dust. So I think this was a really nice case, a nice dust outbreak, at least for me, as I'm sitting here and not in Saudi Arabia, where it truly caused a lot of trouble, but it's an interesting case out of the satellite point of view. So probably not the April weather you expect to see. And now another April phenomenon, not so much an April phenomenon, but a phenomenon that occurred in April this year, was this widespread widespread anticyclone from North Africa over the Mediterranean Sea, Central Europe to the North Sea. So it's really a widespread anticyclone, bringing nearly cloud clear conditions in vast areas, as you can see here in the infrared 10.8. Looks really very clear, as the sky looks very clear. And if you take a look at the natural color RGB, then you can see, really nice spring-like conditions, nearly no clouds over Central Europe, the Mediterranean area. And most of you probably know the natural color RGB. Here's the recipe. So I've already mentioned on the red beam, there's the near infrared 1.6, which is, as I said before, reflective to soil, or very reflective to soil or to deserts. On the green beam there's the visible 0.8, which is mainly reflective for vegetation, so that's why we see green where we suspect green. And on the blue beam there's the visible 0.6. And with the help of the natural color RGB we can distinguish between water clouds, which appear whitish, and ice clouds, which appear bluish, and we can also see snow cover. For example, here the Alpine ridge is bright blue. That's not due to cirrus clouds, not due to ice clouds, but because of the snow. Here the Carpathian Mountains, we see the snow, and also in the central Pennine Mountains you see some blue dots showing you the snow. And in this example you can easily say this is snow. There are no clouds, so this has to be snow. And if you know the orography, it's even more easy to say this is snow. But if you have more clouds, if you have more ice clouds, it gets a little bit more difficult to say these are clouds and this is the snow. So there are other satellite images to use in such cases, and here we jump again to the day microphysics RGB I've shown you before. Here you have the recipe. So, and you see the snowy areas, the Alpine ridge appears now pinkish, and also the Carpathian Mountains. And in comparison to that, the ice clouds, they appear more orange to reddish. So if you use the day microphysics RGB, you can clearly distinguish between snow and ice clouds. And the reason is because for snow there is no green contribution, because the infrared 3.9 detects higher reflectance over small water particles compared to large ice particles. So the snow consists of large ice particles, so there's nearly no contribution from the green beam over here. So, as I've shown you before, day microphysics is a very nice tool to use. We still stay at Central Europe. You see here 3 different RGBs, and if we start with the natural color RGB, it looks nice, nearly cloud-free conditions, some water clouds here, some snow over here, but apart from that it looks really nice. What you don't see, or what you nearly don't see, are the cirrus clouds, the thin cirrus cloud shield over here, because cirrus clouds have a very weak reflection in the natural color RGB. You can sometimes see it over water surfaces because there's a good contrast from dark blue to the light cyan blue, but over the land it's quite difficult to see them. They're quite invisible. If you take a look at the day microphysics RGB, thin cirrus clouds appear greenish. Because of the small particles, they have a good reflectance on the green color beam for the infrared 3.9. So you can see them over here, but they don't look too, the contrast is not too good. And if we take a look at the dust RGB, as I told you before, they're quite useful for monitoring thin cirrus clouds. You can see them very distinct. I mean, you can't miss them in the dust RGB, these black clouds, which are thin cirrus clouds. So, as I've mentioned before, for monitoring thin cirrus clouds, the best RGB product is the dust RGB. And I think this is quite a good example for that. So, in the end, time is flying. We've seen this widespread high pressure center, which brings very few clouds to a great part of the Mediterranean area, Central Europe, and even parts of Northern Europe. But if you take a look at the water vapor 6.2 image, you see, although there are no clouds or nearly no clouds, there's lots of water vapor in the upper atmosphere. And so, yeah, it's always impressive if you see the nearly cloud-free sky and then the water vapor image where you see lots of water vapor nonetheless up in the air. And as the time is running, I just show you the last image, again the water vapor image with the geopotential in 500 hectopascal, and you see this nice omega again over here, which brought the nice weather in the middle of the more or less unstable April. So that's it for today. I want to thank you for your attention with a nice picture from Salzburg. So this is what Salzburg looks like at the moment. Spring has arrived here. Some thin cirrus in the sky, which can be easily detected with the dust RGB. And so, yeah, That's it for the April weather briefing. I hope you enjoyed it, and I wish you a nice day and hope to see you at the next weather briefing.